Okay, in this video we're going to wrap up section 3.1 and we're going to talk about differentiability and continuity. The following alternate limit form of the derivative is useful in investigating the relationship between differentiable and continuous. The derivative of f at point C is, f prime of C, as x approaches C, is simply f of x minus f of C over x minus C, provided that this limit exists. Note that the existence of the limit in this alternate form requires that we have two one-sided limits. The limit as x approaches C from the left side, the negative side, and the limit as x approaches C from the plus side or the right side, those have to exist and have to be equal. These one-sided limits are called derivatives from the left and from the right, respectively. It follows that f is differentiable on a closed interval from a to b if it's differentiable on the interval from a to b, and if the derivatives from the right at a and the derivative from the left at b both exist. If a function is not continuous at a point, it is not differentiable at that point. And I always like to think about, imagine a function where we have a gap here. We're coming along, we have an opening, maybe it jumps down here and the function keeps on going. Is there a derivative at this x value, at this point? Because there's a gap there, because the function is not continuous, of course it's not going to be differentiable. We cannot get a tangent line to measure its slope at that point. Although it is true that differentiability implies continuity, the converse is not true. That is, it is possible for a function to be continuous but not differentiable. The converse is not true. If it's not if it's not continuous, it's definitely not differentiable. But just because a function is continuous does not mean that you can take a derivative at any point. And examples 6 and 7 are going to go into two cases where this happens. Let's see here. First, a graph with a sharp turn. Here we have an absolute value function. The function, the absolute value of x minus 2, is shown in the figure. Here we have it in the figure. Remember, these absolute value functions look like a V or a check mark shape. It is continuous at this point. Remember, continuous, an easy way to think about it is, can you draw it without lifting your pen off the paper? I can, come down this side of the graph and I can hit this point 2 and stop and head up this way. I've never lifted my pencil off the paper, so it is continuous, but is it going to be differentiable at that point? Well, let's see here. Let me slide that picture back out of the way. However, we have two one-sided limits that are not equal. So we're not going to be differentiable at that point x equals 2, where the sharp turn occurs. And the graph of f does not have a tangent line at that point. Let me see. Can I move these over here a little bit? A little bigger. And let's just check this out here. As we approach from the negative side, from the left side, f of x is going to be our function, the absolute value of x minus 2, minus f of 2. Well, what is f of 2? When we plug 2 into the function here, our output on the y-axis is 0. So that becomes the absolute value of x minus 2 over 0, divided by, our denominator was x minus 2, which is, we'll just write it without that minus 0 on there, the absolute value of x minus 2 over x minus 2, which is equal to negative 1. Remember, that's as we're approaching 2 from the left side. If we think about it graphically, down here, here's our value of 2. We're approaching it from the left side. We're coming up here underneath it. And as we're approaching, we're sliding down this part of the line. This is definitely a negative slope. Negative 1 is the slope here to the left side of 2. And as we look at this, as we approach now from the plus side, there is a little plus there. We're approaching this from the positive side. We're going to get the absolute value of x minus 2 minus 0 over x minus 2, exactly what we found before, x minus 2 over x minus 2. And that's absolute value bars. And when we're at numbers greater than 2, this is going to equal to a 1. So let's see here, just to see where these signs differ. Here it's a -1, here it's a +1. Well, for this one I did in blue, we're approaching 2 from the positive side, numbers greater than 2. Well, let's pick a number greater than 2. How about 5? If I plug a 5 in here, I'm going to get 5 minus 2 in absolute value bars. So that's going to be 3 in absolute value bars. And the absolute value bars are just going to leave it as a 3. So we're going to have 3 over. Down here we'll also have a 3. 5 minus 2 is 3. 3 divided by itself is 1. In the first part here, we were approaching from the left side, from numbers less than 2. Well, let's just plug in a number less than 2, 0. Let's plug a 0 in here. 0 minus 2 would be -2 in absolute value bars. And then the absolute value bars would turn that -2 into a +2. And then our denominator doesn't have the absolute value bars. That would be 0 minus 2 or -2. So now we have -2 divided by 2 or -1. And again, graphically, here we were looking at numbers above 2. We got a slope of +1. Well, any number here, any point to the right of this 2, we are on the curve, or the function, and now we do have a positive slope. Here the slope is negative, here the slope is positive. The left and right-handed limits are different, 1 and -1, so that's just saying that we cannot take the derivative at that point. It's not differentiable at x is 2. So we do not have a tangent line right here at that point. So if you have a graph with a sharp turn, you're not going to have a derivative. What about a vertical tangent line? So we have a function, f of x, oops, there it is. F of x is x to the 1/3 power. Remember, x to the 1/3 is also the same as the third root of x. It is continuous at 0 if we were to graph it. And it does say as shown in the figure. I don't think I have the figure out there. However, because, let's just dive in here. We have this alternate form. The limit as x approaches 0, f of x minus f of 0 over x minus 0. Well, f of x, I can replace this with my x to the 1/3 minus f of 0. If I plug 0 in here, 0 to the 1/3, or the third root of 0, is 0, all divided by x minus 0. So what I'm left with is x to the 1/3 divided by x to the 1st. And because the bases are the same, I can subtract the exponents. So that's going to be the same thing as x to the 1/3 minus 1, or a third minus 1 is -2/3. X to the -2/3. And to get rid of that negative exponent, we could rewrite it as 1 over x to the 2/3. And my manners are bad. I did drop my limit notation. The limit as x approaches 0. Now we've got to think back to chapter 2 maybe a little bit here. As we are approaching 0, we're getting closer and closer to 0, smaller and smaller numbers. This could be, instead of x, we could replace that with a 0.01 to the 2/3 divided into 1. 0.00001 to the 2/3 divided into 1. These numbers will get smaller and smaller and smaller the closer we get to 0, and then we're going to be dividing that into the number in the numerator that does not change. A finite numerator divided by an infinitely smaller and smaller and smaller denominator is going to give us an approach to infinity. So this is telling us, our tangent line has a slope that's getting closer and closer to infinity. That is a vertical tangent line. So therefore, f, our function, f is not differentiable at x equals 0, because we would have a vertical tangent line. So theorem 2.1, this is the link between differentiability and continuity. Differentiability implies that you will also be continuous. If f is differentiable at the point, then it is continuous at that point. The converse is not true. If it is continuous, does not necessarily mean it's going to be differentiable. Especially right here, this is continuous. You can draw this absolute value function without lifting your pen off the paper, but just because it is a continuous function, it is not differentiable at that sharp turn. That makes a very good, maybe true and false question for a test, wouldn't it? If it's differentiable, then it's continuous. The converse is not true. So, it's summarized down here below. The following statements summarize the relationship between. If a function is differentiable at the point, it's continuous at the same point. So differentiability implies continuity. It is possible for a function to be continuous at that point and not be differentiable. So continuity does not imply differentiability.